Suppose you were asked to find the deformation of a structure that looked like this, and we load them with both a vector load at the end of this bar and a torsional load also at the end of this bar. And we asked you, what is the deflection and what is the rotation at this end of the bar? Now, of course, you could always CAD it up like I did, run an FEA, and figure out what the deflection and the rotation happen to be. Or we could use something called Castigliano's theorem to sort that out. So what does that deformation look like? Here's an example of what it would do. And I'm telling you right now that with Castigliano's theorem, you could write a closed form solution that would match the deflection that the FEA is generating. So let's get to it. When we look at a complicated geometric shape like we just showed, we have this solid shaft that lies along three separate planes. We have segments in the X, Y, and in the Z direction. And if we go ahead and apply a load to that structure, we will get a deflection of that structure in the direction of that load. So if we have a force F, it will have an associated deflection delta in the direction of F, and that then allows that force to do work which stores elastic energy inside the structure. So long as we do not plastically deform the structure, it is always true that that structure will behave elastically if it's made of a linear elastic material. And if we were to look at the load deflection behavior, we would see that it was indeed linear and it had a slope K. K is an equivalent spring constant for the structure. The force F is equal to K times delta. Now, interestingly, if we were to integrate F with respect to deflection, we would get the area under this curve, and the area under that curve is just stored elastic energy. I'm going to go ahead and call that U elastic. It's just going to be 1/2 the base delta times the height F. Well, if delta and F are related through the simple linear spring equation, then this is also just F squared over 2K. So we have stored elastic energy. We're doing work. So this elastic work term has a very simple relationship to the applied load and the spring constant for the structure. If we take the derivative of the elastic work with respect to the force, we find that it is simply equal to F over K. But recall, F is equal to K times delta. So delta is equal to F over K. So if we can find an expression for the stored elastic energy in a structure, and we take the derivative with respect to the force that's being applied to it, that would then give us the deflection. And this is the basis of Castigliano's theorem. The only complication in Castigliano's theorem is figuring out what the stored elastic energy happens to be. It's also true that if we had a shaft and we fixed one end of that shaft and we applied a torque to it, so we're trying to rotate it, that if you looked down along that shaft, you would, of course, under the influence of that torque, you would have an angular rotation, theta. And so it turns out that there is energy stored in torsion, brought about by torsional loads. And if you take the partial derivative, well, if you take the derivative, if it's only a function of one variable, it doesn't matter whether you take partials or just normal derivatives. But sometimes there can be more than one load applied, and the partial of the energy with respect to any one load gives you the deformation at that load in the direction of that load. So the partial of the stored energy due to torsion with respect to the torque that's applied is going to give you an angle of rotation of theta. All we have to do to utilize Castigliano's theorem is we have to figure out all of the energies, the stored energy associated with all the modes of loading. And so far, we have talked about various modes of loading that include tension and compression, torsion, bending, transverse shear, and direct shear. So we have to come up with expressions for the stored energy for each of these types of loads. So if we go ahead and look at a bar that is fixed at one end and we load it in axial tension with the force F, then the stress that that bar experiences is just the force divided by the cross-sectional area. The strain is just the stress divided by the elastic modulus, so long as we are in the linear elastic range. But we also know that if the shaft is of length L and it stretches by an amount delta, that strain is delta over L. Well, if we were to plot this tensile stress against tensile strain, we get a linear elastic relationship, both loading and unloading. It has a slope that's equal to the elastic modulus, and the area under that curve is just 1/2 the base times the height. Well, the height is sigma and the base is the strain, and the units of that happens to be energy per unit volume. So we have to take that stress-strain relationship in the loaded component and we have to integrate it across the entire volume so that we can get the total stored energy. So the total stored energy is just the integral of 1/2 stress strain across the entire volume. So for tension and compression, the stress is just F over A, the strain is just F over AE, and so the energy density is F squared over twice A squared E, and the total stored energy is going to be the integral of that energy density along the entire volume of the bar. Since the stress is uniform and tensile, the volume is just the cross-sectional area times increment of length. We integrate that over the total length, and we find that the total stored energy is just F squared L, where L is the length of the tensile component, divided by twice AE. For torsion, we find that the energy stored due to a torsional load applied to a shaft is just T squared over 2GJ integrated along the total length of the bar. For direct shear, which loads as shown here, the energy is just F squared over twice AG, where G is the shear modulus integrated along the length. And for bending, the energy due to bending is just the moment squared divided by twice EI integrated along the length of the bar. For transverse shear, is just CV squared over 2AG integrated along the length of the bar, where C is a constant you can look up in table 4.1 in the Shigley textbook. So let's do a quick example of a built-in cantilever beam. So I'm going to have a wall here, and I'm going to have a cantilever beam that is embedded in the wall and loaded at the end with the force F pointing down. You know that once we remove that bar from its support, that we would have a moment, M, and we would have a shear force, F, downward directed force acting at the far end of the beam, a distance of L off to the right. And the magnitude of that moment is just equal to F times L. The moment expression as a function of X would simply be minus F times L, that's the moment at the end of the beam, plus F times X, and that is just F times X minus L. And I know that I also have two stored energies associated with this beam. I have a bending energy, which is M squared over 2EI integrated along the length of the beam from 0 to L. And I have a transverse shear energy. We said that the transverse shear energy was going to be the integral from 0 to L of CV squared over 2AG integrated along the length. V is simply equal to F in this case. It is the shear. And what is C? C is a factor that depends upon the cross-section. So if we have a rectangular cross-section, then C would be equal to 1.2. Our total energy in the beam would be the sum of the bending and the transverse shear. The bending energy is simply the integral from 0 to L of F squared X minus L squared over 2EI I integrated along the length. The force doesn't change. The material doesn't change. The cross-section doesn't change. And so I'm simply going to be integrating from 0 to L, x minus L squared with respect to x. F squared over 2EI, 1/3 x minus L cubed integrated from 0 to L. And that then gives me F squared over 6EI times the quantity L minus L cubed minus 0 minus L cubed. I'm evaluating this at both L and at 0. This first term is 0. The second one is negative of a -1 cubed. That's going to be negative, so it's going to be F squared over 6EI. It's a positive term. The energy always will be positive, and this is going to be L cubed. So there is my bending energy. Now I want to calculate my transverse shear energy, and I've said that my transverse shear is simply the integral from 0 to L of CV squared over 2AG dx. Well, everything inside there is constant, and so I just get CV squared over 2AG x evaluated from 0 to L. So that just gives me CV squared L over twice AG. So my total energy is going to be F squared L cubed over 6EI plus CF squared L over twice AG. So there's my total energy. And the deflection at the end of the beam in the direction of F is simply the partial derivative of that total energy with respect to F. And that just gives me twice FL cubed over 6EI plus twice CFL over 2AG. Get rid of those 2's, and I get FL cubed over 3EI plus CFL over AG. So that is the deflection at F in the direction of F. And you'll notice something. That is, this first term varies with L cubed, the second with L. And so the bending term is a greater contribution to the deflection for long, slender beams. And so what often happens is we often ignore the transverse shear deflection, and that's how you use Castigliano's theorem.